Okay, so this is going to be our third lecture on Kepler's laws. In this case, we're going to be proving Kepler's third law. So Kepler's third law says that the period of an orbit, that is the time it takes to complete a full orbit, is related to the semi-major axis of the ellipse. And this one is sometimes referred to as the law of periods. And the way that it's stated is, well, okay, so let's call tau the orbit period, the orbital period. And if A is our semi-major axis of the ellipse, then the way that this Kepler's third law is stated is that this square of the orbital period is proportional to the cube of, so this is a proportionality here. So tau squared is proportional to a cubed. This is what Kepler stated. And that's what we're going to show now. Okay? And what we're going to do is start with what we showed when we proved Kepler's second law. So we're going to start with our result there. So Kepler's second law result. That is, we showed that the time rate of change of the area swept out by a line between the Earth and the Sun, or a planet and the Sun, is equal to L over 2 mu, where L is the angular momentum and mu is the reduced mass of the two-body system. Okay, so we're going to start with that, and then now we're going to use the area of an ellipse to get an expression for tau, the period of the ellipse. Okay, so let's write that here. So the tau, well, maybe first let's note that the area, the total area of an ellipse is given by that formula. That is, the formula for total area of an ellipse is to take semi-major axis times semi-minor axis times pi. This is just a basic geometry fact. So we have that fact, then we can move forward like this. So we can define the orbital period by just taking the total area of the ellipse divided by the time it takes, or the area per time. So the area per time, right? That is, I'm just going to take this A total and divide it by dA dt. That's how long it takes for the whole orbit to complete. So that is pi AB divided by L over 2 mu. So L 2 mu. So that is the time required to complete one full orbit, right? And at the moment, this says, okay, that time is proportional to A and B, both the semi-major axis and the semi-minor axis. So let's go a bit further here. And A and B are not independent, so let's keep going here and to get to the point of Kepler's third law. So, and we can note that B squared is equal to, so if you go back to the lecture that I had about Kepler's first law, we wrote down the definition of B in terms of the parameters of our orbit in this way, that is, it's c squared divided by 1 minus epsilon squared, which you could also rewrite as c times this semi-major axis A. Remember, c is a parameter that is, it's not an ellipse parameter per se. This is a parameter that came from solving the two-body problem. So c is equal to L squared over mu times k. Or if we go even a bit further, so k is equal to g m1 m2, right? That's our going all the way back to our constants that we started the problem with. Okay. Maybe we might as well write down that mu as well. In terms of our initial parameters in the problem. That's so anyway, keep going here. So then what's tau squared, right? This isn't our Kepler's third law, it's about tau squared. So tau squared, if we take this thing and square it, is just going to be equal to 4 pi squared a squared. And now the b squared I'm going to replace with c squared a squared, right? B squared is equal to ca. B squared is equal to ca, so we'll replace that with a ca. And it's multiplied by mu squared and divided by L squared. Alright, so we're just plugging and chugging here. This is showing that t squared is proportional to a cubed. So I guess we could stop there. That's done, right? That is the Newton's third law now proved. And the proportionality constant here is related to the reduced mass and the angular momentum of the two-body system. So that concludes, I guess, a proof of Newton's third law.